Underwater video enhancement has long been held back by a fundamental challenge. Paired data is nearly impossible to collect. The complex physics of underwater imaging, light absorption, scattering, color distortion, make it incredibly difficult to capture synchronized, high-quality video pairs. And yet, underwater video is essential for marine research, autonomous underwater vehicles, and real-time monitoring. Most current methods take a shortcut. They apply powerful single-image enhancement models frame by frame, then stitch the results into a video. Simple, fast, but flawed. The result: temporal inconsistency. A fish flickers in and out of existence. Corals jitter unnaturally. Color shifts between frames. To the human eye, it's jarring. To machines, it's disastrous. So the core question becomes, can we preserve the visual quality of image enhancement while restoring natural, flowing motion in video, without needing paired training data? Our answer is WaterWave, a novel, learning-based framework that bridges underwater image enhancement into coherent video streams using wavelet-based temporal consistency. Let's unpack how it works. The core insight: temporal consistency lives in frequency. We start with a key observation. Temporal inconsistency isn't random, it's concentrated in specific frequency bands. By analyzing video signals through the lens of wavelet theory, we prove that most flickering artifacts appear in spatial low-frequency regions, with temporal high-frequency components. In other words, large, smooth areas, like the deep blue background, tend to jump between frames, while fast-moving, high-frequency details like fish fins or coral textures remain stable. This gives us a powerful prior. Temporal inconsistencies are predictable, localized, and can be suppressed without damaging motion or detail. The architecture: a wavelet-driven, implicit neural framework. WaterWave is built around an implicit neural representation, inner, a continuous function that maps any x, y, t coordinate to a pixel's RGB value. But unlike standard INRs, we don't just aim for fidelity. We enforce temporal consistency as a hard constraint. Here's how we do it. Multi-scale hash position encoding. To capture the rich, complex motion in underwater scenes, fish undulating, currents shifting, we use a 3D multi-scale hash encoding. This technique generates a high-dimensional positional embedding for every voxel in space and time. Importantly, we apply a hash encoding annealing strategy, a progressive weighting scheme that starts by focusing on coarse spatial and temporal scales, then gradually refines fine details. This mimics how humans perceive motion: first the big picture, then the fine motion. Transmission-guided flow rectification, TFR. Here's the kicker: optical flow estimation fails underwater. Standard models like Raft are trained on open-air scenes. Underwater, light scattering distorts motion cues. Flow estimates become noisy, inaccurate, and inconsistent. So we fix it with transmission-guided flow rectification. We use the atmospheric scattering model, widely used in underwater imaging, to estimate transmission maps from enhanced frames. These maps reveal how much light reaches the camera after passing through water. Then we feed these transmission features into a deformable field network, which adaptively corrects the raw flow. The result: much more accurate motion alignment, especially around delicate objects like swimming fish. This ensures that when we warp frames, we're not warping noise. We're warping meaningful motion. Video consistency-aware wavelet, VC-Wave. Now the heart of WaterWave. VC-Wave, a wavelet-like transform designed specifically for temporal consistency. We apply a lifting scheme, a fast, in-place wavelet implementation, across both spatial and temporal dimensions. The process splits the video into low-frequency components, L, the basic scene structure; high-frequency components, H, motion details and texture. But here's the innovation. Based on our prior, we identify temporal inconsistency by detecting regions with strong temporal high-frequency responses, weak spatial high-frequency responses. In other words, areas that should be stable but are flickering. We extract these via a learnable mask using convolution and Ray-LU activation, combined with an AND gate. The mask isolates the inconsistent components. Then, during training, we regularize this mask, penalizing the model for learning those unstable temporal fluctuations, while allowing it to preserve the true motion and scene content. This is done through a custom loss. Temporal consistency, loss equals L1 norm of the masked high-frequency temporal components. And to ensure fidelity, we also enforce detail loss, difference in high-frequency spatial components between output and input. Basic content loss, match between low-frequency spatial and temporal components. The network learns to suppress flicker without losing sharpness. Why it works: from flicker to flow. Let's look at real-world results. On the UVOT 400 dataset, a benchmark for underwater object tracking, our method improves tracking precision by 19.7% on UOS track and 9.7% on MAT. A massive leap. Why? Because temporal consistency isn't just visual, it's functional. When you feed a flickering video into a tracker, it loses the target. But with WaterWave, the motion is smooth, the object remains consistent, and the tracker sees the truth. In fact, in one case, the tracker successfully recovers a target that was lost in the original enhanced video, because the temporal coherence restored by WaterWave allowed the model to reconnect the object across frames. Quantitative validation. On no-reference metrics like CLIP-A and NIMA, WaterWave consistently outperforms state-of-the-art methods, CODA-F, DVP, and others, across multiple UWIE backbones, both DWN 5A+. Even more telling, our method maintains spatial enhancement quality. Unlike some approaches that smooth out details to reduce flicker, WaterWave preserves the original image enhancement while fixing the video. And in progressive training, we see a clear pattern. Early iterations, spatial details are learned first. Later iterations, temporal consistency emerges, flicker fades, motion stabilizes. This proves our method doesn't just add consistency, it learns it from the data. Limitations and future work. One caveat, because WaterWave is an implicit representation, it's trained per video or scene. So scaling to many videos means longer training. But here, as a promising path, we can generate pseudo-video ground truth for training other video restoration models, solving the paired data bottleneck in a new way. In future, we'll explore using WaterWave to bootstrap video models in low-data regimes, opening doors for real-world underwater applications. Conclusion: WaterWave isn't just another enhancement pipeline. It's the first learning-based framework that explicitly models temporal consistency in underwater video, using wavelet theory, implicit representations, and underwater-aware flow correction. By rethinking the temporal manifold through frequency, and designing a system that learns to suppress flicker without losing detail, we bridge the gap between image enhancement and video realism. And in doing so, we unlock new potential for downstream tasks, from tracking to navigation, proving that temporal consistency isn't a side effect. It's a foundation. So the next time you see a fish swim through a coral reef in a video, ask yourself, is that motion real? Or just a flicker in the data? With WaterWave, we're making sure it's real. The code is open source. Check it out at github.com/zqcraft/waterwave and help push the frontier of underwater vision.